Here we go with work, energy, and power. Do make sure that you are using your little formula sheet packet. You can add formulas to this, but you do want to have it in one spot, especially since, as you see, these modules are going to be building and you're going to be using stuff from most modules all together. So that module 4 test is kind of like a midterm, not going to lie, even though we don't have a midterm. So make sure you're keeping it all organized. So here's your main units and your work done here. Make sure that you have written down in there how work is seen as positive and negative. Okay, since work is force times distance, if you don't move any distance, your work is going to be 0. So if you're pushing against the wall and the wall doesn't move, you might be exerting a lot of energy, a lot of force, but you're not moving any distance, so it does not count as work. Right. So in this case, we want the difference in the work. So we're going to have to subtract when we get to the end from lifting 100 kilogram dumbbell. So that's a mass from the ground to a height of 2 meters versus a height of 1.5 meters. So I have 2 different heights, 2 different scenarios. I have the dumbbell. I'm lifting it up 2 meters here, same dumbbell. I'm lifting it up 1.5 meters there. What's the formula? I need work, so that's force times distance. Work equals force times distance. When you're looking at this dumbbell, the work that we need is in the y direction. So the work in the y is equal to the force in the y times the distance in the y. What force do we have here that we have to overcome? We have to overcome the force of gravity. So the work is going to equal the force of gravity times the distance, or in this case, the height. 100 times 10 times 2, 2,000. Okay. Work over here. Again, we have the force of gravity going down. If you were drawing the full free body diagram, yes, you would have the force of applied going up, and we'd know the force applied equals the force of gravity. But we need to know how much energy to expend to lift up that pebble. So we're going to be again concerned with the y direction force of the force of gravity and a distance in the y there. 100 times 10 times 1.5 is 1,500. We're going to subtract those two for the answer. 500 joules. 500 joules is the units that you would have here. Joules are newtons times meters. Why? Force is newtons, distance is meters. So Newton meters would be your answer there. Okay. You can also look at it a different way, as I have it written up here, as the force work, the change in work is the force times the change in distance. And that's what we're going to be using a little bit later on. I did want to show it both ways so you can start getting familiar with using that delta sign in this case. You can only do that if both the forces are equal. So if you have 2 different weights, you cannot use this second set of problems. You would have to just directly compare if it's 2 different weights. So you'd have 2 different forces. Tyler expends 80 newtons, so that is our force applied. Moving the 10.1 kilogram box, that's our mass. 50 degrees, that's our theta. Coefficient of friction, that's our mu. Traveled 5 meters, that's our distance. Notice we're going to be concerned with the x direction here. So this is the work in the x direction. So it's going to be the sum of the forces in the x times the distance. Draw your free body diagram. The force applied is at an angle, so you're going to have to break it down into its component forces. Force applied in the y is force applied times sine theta. Force applied in the x is force applied times cosine theta. Hopefully that's starting to get situated here. What are we going to do? We're going to sum the forces in the x and the y again. Okay, and we do have our force of gravity down there. Hopefully that one is getting to be super easy to recognize. Force of gravity is mass times gravity. Okay. force of friction, that other standard one that you're going to put in, and then we know that's 0.01. We already have that first part. Force of friction, 0.01 times the force of normal. Hopefully that other basic equation is getting like clockwork to write down. Okay. Why did I solve it this way? Because I know I'm going to need my force and normal for later. If you don't know that, then still do it the old way. Force and normal plus force applied in y minus the force of gravity equals 0, and then rearrange. There's no problem with still doing that extra step from the earlier modules. And then the force applied in the x direction is the force applied in the x minus the force of friction equals the force in the x. In the earlier modules, we are saying equals mass times acceleration. If the problem needs me to find acceleration or needs me to find the other velocity, yes, I would need that part, but I don't need it here because I am concentrating on just needing the force in the x for my answer. And so now I can go through and solve this problem for the force of x and substitute it into my work problem. And so that is kind of the full build up of this unit. Notice if they do not give you your mu for the just this first lesson, you can say assume the force of friction is 0. Later on, we're going to show you different ways to work around that, but that is something that can happen just in this module, but make sure there's no other way for you to solve it at this point. And that is all. Have a great day.